gentlemen, good afternoon. Welcome back. Thanks for all being back on time. We have now till the break 5 presentations with 3 speakers. They don't need any introduction, they've all spoken this morning. So I'd like to invite Graham Monteith to come back now and talk about setting up the site next.
Hello again. So this next section is entitled Setting Up the Site. There's very few words on these slides. It's just a lot of photographs of various microtunneling setups that I'm just going to talk around and highlight some of the issues and things to consider. In considering how a project is conceived from design through to actually delivering it, there's a lot of things that need to be considered. So the operations take the constraints on the site, the risks associated with the constraints on the site, access, egress, emergency vehicle access, anything you could think of on any site. There's nothing particularly specific to pipe jacking other than shaft size, and I have a section on shaft sinking later, so I'll talk through that later. Have you got close neighbours, noise, dust, all that stuff. So pipe jacking is a very flexible and non-disruptive method of installing a conduit between 2 points, and hence it gets used in typically in heavily built up areas, or where there are major services that need to be crossed and can't be easily diverted, under rivers, under railways, and sometimes in areas where there's a triple SI or some other feature that needs to be crossed. In urban environments, then the shaft size is pretty critical to what you can and can't achieve in a narrow road. So some of us Trent people in the room might recognise this. I actually got that off Google Earth, so it's public domain. This is a photograph of one of our recent sites on the Birmingham Resilience Project, which is a 40-kilometre pipeline. And this is one of the crossings that we had to install. The constraints here were route, so we had a route constraint. This area here is a triple SI, it's a flood meadow, and underneath that triple SI is a geotechnical triple SI where the actual ground conditions underneath the ground are protected. I've never come across it before. And the boundary to it is just on the side of our tunnel alignment. We then have an industrial estate. We've got the River Stour here as part of the crossing, an A road, and then a rather difficult land tenant here who has a motorbike track. So you would think at design the right solution is to take that shaft off the hill. So you can't, I've got a section in a minute, take that shaft off the hill, put it here, shorten the drive, but no, we couldn't do that because of this tenant who owns that ground. So we've got access issues through this residential street into an industrial estate with lots of tenants. We had to build a bailey bridge over the river to gain access to the field. There was a kestrel nest in that tree that we couldn't go within so many metres of. These are just examples of things that crop up in terms of planning. And this is the drive shaft location. So because of where we are, there are no sewer disposal points for wastewater. The shaft is in sandstone with high water table. So we had to sink that shaft to, I think it was 35 metres deep as an underpinned structure with deep well dewatering to control the groundwater. These two holes here are the water lagoons that we had to put the water through before we could polish it with another system in order to get a discharge to river consent. So it's a particularly difficult site. And just illustrates some of the problems. Now, that's in an open kind of field position. Imagine some of those constraints if you're in a town, and what you might need to do to overcome it. One of the advantages is, though, that we had, once we got in there, we had as much space as we could possibly want. So this is a section drawing of that same crossing. In fact, no, this is the next crossing, sorry. That's a close-up of, I've put the drawing in the wrong place, I'll go back to it. So that's a close-up of the site. This is the pipe stringing area for when we finally sleeve through the tunnel. Site access, so we've got separation plant, area for spoil management. This is the water management area. Pipe store, crane, site office, various other bits and pieces. Now that's very luxurious in terms of area, and we don't usually get that kind of room to use. This is the right cross section. So this is the cross section, very deep shaft in sandstone with its constraints of dealing with groundwater at depth, river with superficial deposits, a very steep drive to an equally deep reception shaft. By bringing that to here, we would have probably saved £1 million, but the constraints wouldn't allow that. One of the interesting things to see here is the change in the topography and how that impacts on cover to tunnel and the groundwater profile. So the groundwater roughly follows the hill. So the worst position for overpressurisation and loss of fluid is actually halfway up the drive where we've got minimal cover. And we had to be very careful how we drove that tunnel and controlled face pressures. One of the other problems was the setup in the shaft bottom. We're driving uphill with 3 bar of water pressure, and every time you push the pipe forward, unless you actually put in a brake, which is to grab the pipe, it just wants to slide back out of the hole into the shaft. So this shaft had a pipe brake in it. I'll just go back to that other drawing in a minute. So this other drawing is the next crossing, which was just up the field. It has similar issues, but they're not quite as pronounced. But if you notice all these hazard drawings, these are all constraints on the design and delivery of this project. And these here, there's actually an old landfill tip which has radioactive thorium in it. So we were tunnelling under a radioactive site, and actually managing and monitoring and controlling that risk during the tunnelling operation, and actually convincing people that we could do that safely was an interesting problem. So this is, again, is a picture of a site in Welwyn Garden City where we have unlimited room, but it's very, very exposed. It was on top of a hill next to a light aircraft facility, and we had wind problems. So one of the ways of mitigating the wind problem with craneage was to use a gantry crane. We could only really do that because the site was very large. It also meant that the planes didn't fly into it as they were on final approach on that particular shaft. But again, you can see the pipe store under the crane, shaft top. That's the control room for the operator. The control room is always situated next to the shaft so that the operator can actually look out of the window and see what's going on down the shaft. In particularly deep shafts, you would use cameras in addition to that, so you probably have a camera at the top of the shaft and one at the bottom watching the operation. It's also important that the operator can see the separation plant and he can see the discharge from the separation plant, because one of the feedback tools that he uses is watching the spoil come off the separation plant as he's tunnelling. It gives him a good feedback.
I was just going to ask, is that temporary load you have to account for having that containers in the shaft?
Is it a, sorry?
Is it a temporary load you have to account for having that container?
Not really. I mean, it's sat on the
It's about 5 ton.
It weighs very little in terms of loading, and that shaft was sunk as a casing, so there's a big donut of concrete around it, plenty of bearing, so you wouldn't really need to consider that. And then this is the other extreme. This is a project in London, in Stratford, near Stratford, where we're on an old Victorian street. So these are Victorian terrace houses, and we've had to close the road because there just is not enough room to get everything in there that we need to. So again, you've got a service drain, the separation plant's off to the side to allow an access route, and this is obviously before the TBM is actually being dropped into the hole. And that's one of the other manufacturers' machines. That's an Iseki unclog roller, it's called. It's a soft ground machine. So you've got very limited access, very limited storage for pipes. But because we're in London, there's a big sewer system, so we've got no problem with water disposal should we need it, etc. But again, site kind of wagon movements are exacerbated by this site because you've got to deliver pipes just in time because you haven't got room to store them, and you're spoiled, you've got nowhere to keep that either, so you've got lots of wagon movements to manage. So in terms of an environmental impact study, whilst pipe jacking reduces your impact to localised working areas, you've still got all of those plant movements and wagon movements to deal with. This is the same site. So in order to get the machine down the hole, we need to bring in a much bigger crane, which means that access has to be cleared before we can drop the machine. Then that crane goes away and the next crane comes in. So you're constantly cycling equipment in and out of the site, which has program implications, obviously, and might mean that you don't get quite the same kind of production in a confined site as you might elsewhere. And that's an Iseki microtunnel machine.
Didn't recognise it, sorry. That's more like it.
And there's an air connect, yeah. So again, it's another view of another site, control cabin over the site. These are your slurry lines going down from the separation plant, and that's the.
There's the advertising on the side.
I think that's the back. That's the tele. Is that? That's the pump cap.
The middle can.
Yeah, the can. And this is a lubrication mixing plant. So as I was saying, a key kind of component of the feedback to the operator is being able to see the spoil, and this is spoil coming off the coarse screen, so you can see the granular material there, and this is the clay and silt that's being taken out by the centrifuge system. This pod here is where we mix the flocculants, so there's two barrels in there which are constantly filled with flocculant, and the flocculant comes out into the spoil. So we'd often bund these areas because there's quite a high water content, and you'd bump the water off the side. So shaft bottom setups and things to consider. So we've got two accesses here. We've got a walking stepped access and a ladder. So should one become unusable, the other can be used. And of course you've also got the crane at the surface. So you should always have two forms of access to any shaft. And preferably 3 with a crane, because the crane would be used to recover a casualty. Unless he's walking wounded and he can come up the steps. But to put someone on a stretcher, you would need craneage or a davit arm. Sometimes on small shafts we use a recovery arm, like you would do for sewer access. You would often have pumps in the base of the shaft. This drive's obviously got a charge and a discharge pump. I'm not sure why that ladder's up the back wall. It probably shouldn't be there, if we're completely honest. Some of these photographs are probably a little old. And this is a view again of a much larger muck handling bay, where these, what do they call those?
Retaining wall.
L-shaped.
Retaining wall unit.
Yeah, retaining wall units are often used to form a bund. But these are extra large because we've got residential properties out here. This is the site cabin. So these are used for both retaining the spoil and noise reduction. So some of this is also about, there's a big overlap. And I guess if we could wait until the end of the shaft sinking section, I'll take questions on setup and the rest. And I'm probably going to cover a few things that Jim's already been through on the design considerations. So as we've said, I think we've majored on all day. The biggest thing to consider is the geology and the groundwater regime on any site. And the shaft sinking method that you choose will be heavily influenced by both of those things, along with the final application of the structure. So Sewers for Adoption might say we want a 1200 diameter manhole on a 450 diameter pipe, but what the contractor needs to install the 450 diameter microtunnel is probably a bigger shaft. Well, it definitely is a bigger shaft than 1200. You'd be looking at maybe 3 metre diameter. So the final application might impact the size of the shaft, or the actual method of installation might impact the size of the shaft. But of course, as a client, you get more storage if you get a big shaft. The required footprint. So some shaft sinking methods will be very easy to install in small sites. Others are far more plant intensive and need much bigger room. So your site size influences the choice of solution. The depth of the shaft has a big impact on method. So sheeted pit, relatively shallow, shaft sinking machine 100 metres, and there are, and I'll go through all the different kind of range between the two.
Need 2 football pitches to set it up.
Yeah. And cost should be a secondary issue. It's usually a secondary issue. The physical constraints and risks and how you can deal with the ground conditions is by far away the most important thing in terms of shaft sinking method. So I've done a list as well. The only thing that I've got on there that Jim didn't have is the cast in situ case on, which the Wardenburg rep I think is going to say a few things about. I've got a few. Brian told me you were, but I think in your case study. One thing about sheeted pits, and specifically slurry microtunneling, another reason for having closed corners is that your slurry system is the way that you remove ground from in front of the machine, and if you can't remove ground from the front of the machine, your tunnel's stopped. So if you're approaching a sheeted pit which is not closed, the slurry will take the least path of resistance, and at some point it will frack out into the shaft, and then you can't dig. So that's a really good reason for having if you're going to use pits, close them off. Also, one thing about pits and cost, on the face of it they appear relatively cheap. However, for a drive shaft, by the time you've put the pit down, shuttered and cast a back wall, shuttered and cast a concrete front wall, and all the time that's involved in doing that, they often are not as cheap as you might think, depending on depth, whatever people say. So sprayed concrete wasn't mentioned either, so this is only really suitable for competent materials and relatively dry ground. It's not often used in microtunneling. It's usually used for bigger or more complicated shapes, although we have used it. And then the other options I'll go through as we go through some of the pictures. So I've chosen this as an interesting example of a thought process around choice of method. So this is the West Coast Main Line railway, and this is a 600 microtunnel, and it's a twin crossing, so there's two crossings one next to each other. The choice of shaft sinking method is interesting here because we have the River Trent is not far over here, and this is the River Trent alluvial deposits, so it's a mixture of sand, gravel, silt, peat, rubbish. It's not particularly a bad tunnelling material, but it's not the best. And then underneath that we've got this is weathered mudstone on top of mudstone on top of a band of very hard siltstone. So we've got high water table, very hard material, and the constraint of settlement on the railway. Now, in order to put that shaft down and get through the siltstone to get into the mudstone as a tunnelling medium to minimise the settlement, we've got to deal with the water. And because we're next to the railway, we can't dewater this ground. And dewatering is very inefficient when you get to an interface. So we could have put wells in here, but we would still get water running off that interface into the excavation. So we couldn't really, or the risks associated with converting from a flooded caisson, getting a cut off with a cutting edge, and then converting to underpin to deal with the hard ground is a difficult thing to do and adds risk to your. So if we start losing ground at the interface, then we're causing risk to the railway, and it's very close. So a number of options were considered. One option which was considered was a contiguous or secant pile shaft where we sink piles, but that involves a very big rig coring through very hard material next to a railway, and then you've got the collapse radius of the rig onto the railway, which is another problem to deal with. It's also very, very expensive. So the solution that came out of all of this was to sink a flooded caisson shaft into the top of the mudstone, but not relying on the mudstone for cut-off. We then prefabricated the reinforcing cage, divers cleaned out the base, we dropped the cage in underwater, and then we poured the base plug underwater. That allowed us to thin the slab to an extent that we still had sufficient cover in the alluvial deposits to make the settlement calculations on the railway work. Similar thing on the reception shaft. And the breakout, break-in here was dealt with by using a GRP sandwich on the outside of the shaft, rather than putting a concrete wrap on the shaft. At small diameters, you can use they're about 25 mil thick, and they're sufficient to resist water loading over a small span when you're launching a small machine. This is the same crossing, so this shows you the settlement prediction, shaft location, and the twin 600 crossing. So one of the things to consider when doing the twin crossings are not that common actually out of single shafts. But one of the things that drives the diameter of that shaft is the spacing between the two crossings and the physical space within the shaft. So as you spread them out further, obviously the shaft has to get bigger to accommodate that. And the spacing between the two tunnels is influenced by the combined effect of the settlement of the two troughs and what's the best shape of trough for the railway. And it's also influenced by the fact that once you've installed the first tunnel, there's an effect whereby that first tunnel causes a little bit of relaxation in the ground. So if you try and put a tunnel very close to that first tunnel, you often have steering problems whereby the machine wants to drift into the less consolidated ground around the first tunnel. So you need a number of diameters between each crossing. I can't actually read those. Yeah, the green line's 1 mil, and the blue line is 18 millimetres, but that is a combined effect from the shaft sinking operation and the tunneling operation, which again needs to be considered because they do. It's a cumulative effect. So here's a couple of pictures of some sheeted pits in action. This is an Ackerman machine. It's an American machine. It's a very simple, open face drum digging machine which is used in dry, cohesive soils. We've used it in sand as well, but so there's no issues with groundwater here because we're in cohesive soil. But I do notice we've got closed corners on this pit. And this is a sheeted pit that was sunk in rock actually, but for very good reason, because we didn't have room to actually get the right footprint with a circle. We've had to cut the corners off, and obviously we can't do that with a circular shaft. This is in a project in Albrighton, and it was a sewer replacement. So if you notice this black line here, that's a sewer diversion of a major trunk sewer above where we're actually tunnelling. So we had to go down, break that out, divert it around before we could even get down to the base here. And that's another reason for using sheeted pits, because it's a flexible support solution. It's worth talking about sprayed concrete because it's a very flexible and useful way of supporting shafts. These two pictures are the same shaft. They're on the National Grid cable tunnels project that Costain did a number of years ago. Yeah, and Mr. Dexter worked on as well in his previous incarnation. So it's using robots to spray concrete onto in this case it's clay, it's a London clay. Sprayed concrete is a fantastic method, but it does involve quite a lot of QA and QC. And this picture is an above ground test panel spray. So we're filling these little boxes with sprayed concrete, which are then used to test early strength gain, etc., to test performance before we actually use it in anger in the ground. So for small shafts and for pipe jacking, unless there's a really good reason for it, it's probably not the right solution. You can buy bagged, certified shotcrete that performs to a certain performance criteria, but it's quite expensive, and again the flexibility is not particularly good in small diameters. So this is a couple of pictures of precast segmental shafts being sunk as caissons. So around the top here you've got a number of hydraulic rams. Each of these rams is capable of 50 tons of pressure to push down. But generally, they are used for steering the shaft more than they're used for actually jacking the shaft into the ground. especially in dry conditions. And these are quite large shafts, so usually if you count the number of rounds, that'll tell you what the diameter is. I haven't done that. I think that was a 15-metre diameter shaft. I think that's also national origin. And this is just a different view of the same shaft. Worth pointing out, these rings have got internal bolts, so they need to be built from a building cage. There are now options to have bolts on the back of the shafts, which is a much safer solution. But it's not to say that this isn't a valid. We're actually doing a project at the moment in Barrow, in Furness. I can't really tell you where it is, but we're sinking some caissons over magnetic anomalies that fell out of the sky in 1940 something. And we're using internally bolted rings because we may need to actually remove the bolts after we've finished the shafts. This is a cast in situ circular caisson shaft. I've seen square structures built like this, but Warren Burke, who are one of the PJA members, are over the last few years have pioneered this. This is a shaft sinking solution. It's a very smart, impressive solution. It's spirally cast, if you notice, which means you get a continuous process. In the past, caissons were cast in lifts, which is not a continuous process and therefore not very efficient. It's a very smart solution. So this is a precast concrete underpinned shaft. Because it's underpinned, your bolts have to be on the inside because you've got to access them. Basically what you do is you excavate the ground deep enough to take a 1 metre segment, so you might dig 1.2, circa 1.2, and then the segments are lowered down the shaft on the building frame, and this is a counterweight to keep the segment level whilst you build it. In poorer ground than this, you might end up just excavating enough to build one segment at a time. In good ground, you can excavate the whole thing. And that's just a different view of the same operation, a little bit closer up. And again, that's only suitable for dry, cohesive soils, really. And this is another picture of an underpinned shaft. This is actually one of the shafts I showed you a photograph of the site earlier on the BRP project. So this is 36 metres deep. 36 metres is beyond the reach of hydraulic grabs, extending grabs. So it had to be done as an underpinned shaft. And it's in sandstone, so we've got very little groundwater in here because we've got the deep well dewatering on. Any deeper than that and you start getting into the need for some of the specialist kind of measures. So these are two pictures of the same project. This is Newark again. This is the pumping station, large pumping station shaft, which was a 20 metre diameter. Contiguous piled structure, and I'll tell you a little bit about why that was chosen as a method. And this is the main tunnel launch shaft, which was 12 metres in diameter, same depth. This shaft had to accommodate a microtunnel which went under the railway to provide the final connection into the pumping station, but it also had to accommodate a 2.85 segmental tunnel drive in the opposite direction. So the reason it's 12.5 metres in diameter is to accommodate the larger diameter tunnel and the space that needs, rather than the microtunnel. In Newark, we've got the, as I explained before, we've got the superficial deposits over the Mercia Mudstone, and the Mercia Mudstone has gypsum bands within it. The gypsum bands contain water, and they've got a direct connection to the Trent and the ballast above. And one of the problems with the gypsum is when you first excavate a shaft in this material, you might get a little bit of weeping through the gypsum. But as that water continues to flow, it erodes the gypsum and the flow gets quicker, and then the gypsum erodes quicker and then the flow gets quicker, and unless you're very, very quick, you can get into a lot of trouble with groundwater control. And that's one of the main reasons in terms of, so this shaft is right next to the Trent. And that's one of the main reasons we sank it as we did, because you get complete cut-off of all the gypsum bands. There was a little bit of flow in the base, but nothing that couldn't be handled. The same reason was, so if we did it there, we might as well, we've got the rig on site, we might as well do the same thing here. So the difference between secant and contiguous is subtle but nonetheless pertinent. If you were in very dry ground, then you could use secant because they don't interlock. They just butt up against each other, but you can get leakage between the two. And a contiguous pile is a pile that's sunk, hit and miss. So you get two soft piles and a hard pile. And the hard pile goes straight through the two piles either side of it, so you get a cut-off in theory, subject to verticality. And then there's all sorts of different hybrids. You might sink a sheeted pit to get around some services, and then within that sink a caisson or an underpin shaft, or in this case you might use sprayed concrete to form an under-reamed base. So the reason for doing an under-reamed base on a shaft is if you want to mobilise ground weight to reduce base plug thickness. It's a very efficient way of reducing flotation. In this particular instance, this is a project in near the Wirral, and we had artesian water beneath the base. So taking the base plug very deep reduced the clay that was beneath the slab, and then the dewatering that was needed to reduce the artesian water pressure in the temporary state to prevent that base from blowing was far worse than it would be if we thinned the base. So that's the reason that under-ream was actually put on that shaft. Most shafts will need a base plug. If you are sinking a flooded caisson shaft where you leave the groundwater in the shaft and you excavate through the water, you've done that for a reason. It's because there's groundwater there and you can't dewater. And in that instance, you would need to pour a plug underwater, so you'd pour the base plug through a tremie pipe. Ordinarily, it wouldn't be reinforced; it would just be over deep and a mass plug. Because obviously, the other advantage of having a mass plug is weight, because you've got flotation problems. They will pop out of the ground. I've only ever seen it happen once, but they will pop out of the ground. In fact, we made a bit of a mistake on the job in Wales.
I wasn't going to say.
before Dexter dobbed you.
Yeah, but for the grace of God, go on.
Yeah, absolutely. So there was a temporary works design performed for a shaft next to a river, and the temporary works design required the collar, which is a big, in fact, yeah, you know where the rams were in that picture. It's a big concrete donut. So before we were to after we poured the base and before we pumped out the water, we had to dowel the collar to the shaft to mobilise that extra weight so that the thing didn't pop out of the ground. Guess what didn't happen? The temporary works design didn't get transferred into the method statement. The method statement didn't have must dowel collar before pumping water out. Pit boss went in on a Sunday and thought, well, that shaft's been in there, that base has been in, it must have gone off by now, I'll start the pump. Started the pump, no supervision. We had a grand designs kind of thing.
The phrase lighthouse kind of.
Yeah, it was remarkable. It's not something to repeat. And that's site setup and shafts. If anybody has any questions.
Can we go to quick questions for Graham?
I have one small one.
Okay.
I know.
I've heard that.
On the BRP, the pipe jack with the golf course and the idiot with the motocross
Yes.
side,
Yeah.
why didn't you do a flat drive with a curve uphill?
Because that's just overcomplicating things.
Okay.
Dicky. To be honest.
35 metre deep shaft, shaft.
Yeah, I know, it was considered, and it's a long drive.
Yeah, it was 500
Yeah,
metres.
it's 500, I think it's over 500 metres, and driving it like that was deemed to be probably a step too far. We weren't brave enough, maybe. I probably could have done it, but
You
not
had gyro on the machine.
we were carrying most of the risks.
Yeah, well, okay.
Okay. Any more questions? Right, we'll crack on back to Jim Kirby.
Okay, the final kind of session from me on jacking load and backwall design. So we've spoke about this in this morning's session. So I just wanted, it's obviously the whole process of pipe jacking relies on pushing the pipe string and the machine forward. So the thing that you're using for the reaction is pretty important and pretty key to it all. In terms of design variables that you're looking at when you consider the back wall, you obviously it's a thrust wall, so it's this part of the operation here that provides the reaction for the jacks. Again, you have to think about the pipe design that I mentioned earlier on, and we've had obviously the presentations on both the concrete and the GRP pipes. You can't just push, as I said earlier, you can't just push whatever tonnage, whatever pressure you might want to, because the pipes have got they've got a limit on what they can take. Interjacks, we mentioned those a couple of times. Again, the one on that little schematic, this is showing the back of the pit and the main jacks, and then there's a brake and the interjack. So again, when you're thinking about the jacking loads in terms of designing the back wall, you need to understand what you're trying to limit the load to, and indeed how many interjacks you think you're going to use along the line. Friction's probably the biggest factor in it all. So as you push, if you push the pipe along the proposed route, the machine is cutting an anise, and you might have a lubricant in there. And that lubricant might be supporting the bore, but it might not. And I think Graham mentioned that in gravels you can very often launch the machine and just be dragging gravel. Particularly in a granular material like that, you can start to get quite high friction loads, and you can soon run out of power. I've just mentioned that you would use the lubricant in line with the consideration of friction, just to try and offset and get the benefit. Spoil removal can have an effect as well. Now, we'll show you in a little while some extracts from the Pipe Jacking Association Design Guide. So, generally speaking, in terms of the loads that you look at when you're thinking about a back wall, there are kind of there's three areas. There's the friction, which I say is probably the main, the main contributing factor, and then you've got potentially some load from the face, some face pressure. So if you're using a slurry, for example, and you pressurise that slurry chamber up, there will be a load coming back onto the machine, because you're trapping that liquid, if you like, between the ground and the machine. So there may be a nominal amount of load in there. And then also, people refer to it as face load or earth load. So if you think that's not the right picture, but if this was the TBM, this was the tunnel boring machine at the front and the shield, you tend to get a bit of load from resistance on the cutting edge down the actual can itself, because you're not lubricating through that section, and then from the lead pipe. So there's kind of three areas that you pick that load up from. But the specific type of engineering that that you're looking at can affect the loads. So in terms of what the loads are, as I've just mentioned, it's face loads. The calculation takes into account the pipe string weight, so the physical weight of the pipe itself. The friction load, misalignment that we've heard about earlier, so there's two little graphs there, line and level. I think these are probably the old limits now. It's saying 75mm tolerance on line and 50mm on level. I think that's 35 and 50 now. But you can see as you start off, the pipe string may deviate, and as we've said, if it deviates, then you'll start to load the pipes kind of off square, eccentric loading, and that will reduce the amount of load that you can put through each pipe, and the cumulative effect is your overall jacket load will start to increase. Time delays. So, and I suppose this is linked in a way to friction, but the whole idea of the pipe jack is that you're creating this hole and you put in the TBM and then you put in the pipe string through there. Now, if we take a clay, because it's a good material to think about, you excavate that hole and there will be a stand-up time. So you would expect that when you've excavated the bore, there will be maybe a day, maybe 2 days, maybe 20 days before that material starts to kind of come in on itself. I'm told that's true of any material. So, for example, even if you took a solid block of steel and you drill a hole through it, it's infinitesimally small, but that will want to come in. So, obviously, if you start pipe jacking and you have got 100 metres in the ground, and then for whatever reason you get a problem, it could be the weather. Maybe the cranes can't operate because they can't lift. It may be the power pack goes down. It may be a problem with the machine, something else. But if you stop, obviously all the good things that can happen, for example, they can close the valves and make sure that they've got the lubricant trapped in the annulus and try and keep the pressure up there. But obviously if you're delayed for any amount of time and you start getting lost there, then that ground wants to come in. So if the ground comes in and ultimately grabs hold of the pipe, then that then increases the friction load. And very often, I think the startup loads can be quite considerable to get going again. The PGA design guide suggests a rule of thumb of 0.5 to 2.5 tonnes per square metre in terms of friction. It is a rule of thumb. You can look at it in different ways. You can actually get the side investigation. You can look at friction coefficients of the ground. There are a number of ways of looking at it. Throughout the document that's to talk about, there was a lot of research done by a chap called Haslam at Liverpool University, and he looked at various ways. So he looked at a stable bore with the pipe theoretically floating in this medium of lubricant. So in other words, you cut the hole and you pressurise the annulus and the pipe has effectively got no load. Interestingly, when Graham showed the graph earlier on of one of his tribes where there was hardly any load whatsoever, that's the kind of evidence that might suggest you've almost reached that kind of state. You've then got an unstable bore, and then you've got a case that he looked at where you maybe arguably the most common, where you've cut the bore and you've got the pipe, and actually the pipe just sits on the ground, so that the bottom of the pipe is scraping along. So in other words, you've got a contact area of whatever it might be on the bottom, and then it's just lubricant around the top. So construction factors which affect the load are monitoring operation. You need to make sure that you're monitoring the pipe jack itself, line and level as you go along. That's carrying out main survey and control checks, and certainly if you want to start jacking on curves, depending on the system that you're using, those survey and control checks become even more important. It's worth noting that when you're going around the curve, and the digger picks up later, I think, it's not, we do it in the UK, it's perhaps not something that is at the forefront of everyone's mind. Certainly, across the world, people are a bit more adventurous. And there's various things that you can use. There's a thing called a hydraulic joint that you can actually use in the pipes, which is a series of series of tubes that can be inflated on each joint, like mini interjacks almost. But again, survey and control checks are quite important. They keep you on line and level. Understanding the position of the shield is critical in terms of the monitoring, in terms of where you think you're going. And then sometimes the pipe can have a tendency to roll as well. You tend to excavate the ground in different directions to keep the machine, if you like, on its plane. But if you start to get rolling and you start to get misalignments on line and level, then all of these things can increase the jacking load. And then of course, there's measuring the load on the main jacks, on the interjacks, and on the shield itself. And all that needs to be backed up by surface checks. So in terms of the thrust wall, it takes it can take the full jacking load. Certainly when we design, we will look at the drive length, we'll undertake some estimations and look at the friction. And then for a 100 metre drive, we'd work out the maximum jacking load that we thought that we were going to get. And we'd then compare that against the capacity of the pipes. And then that would allow us to work out whether or not we're going to need interjacks. As Graham said, I bow down to others in terms of the actual number, but certainly there'll become a point where even if you don't think you need an interjack, you put one in the line, probably just to be on the safe side, because of course once you've run out of steam, you've run out of steam. The key risk is failure of thrust wall. I mentioned earlier about making sure that the pit's tight, making sure the back wall's good. If the back wall starts to move, then you're going to compromise the whole system. There are varied solutions for different conditions, but ultimately, they're in its simplest form, they're designed as a pad foundation. So if you think about that and turn it on its side, it's kind of a simple bearing failure analysis. So just looking at some different types, just to give you an idea, I've got some photos and some shots. So a sheeted pit, so we've got, there's the sheet. So this is the back wall, the machine is to this side, this is the back wall and this is the plate, so that's the thrust. And you've got a bearing surface that comes down the back. So just some examples, so you can see that. So on this particular issue, this particular scheme, that is the back wall in there. And this one, the back wall is under that plate there. But these are both sheeted bits, so again, sheets with full interlock on the corners. I've got an underpin shaft. This it's probably the wrong terminology. Well, it is the wrong terminology. So this is it is an underpin, but it's what people would call a back shunt or maybe a front shunt. So if Graham talked about sometimes the site can be constrained, so you might have a smaller shaft than you really need to be able to launch the machine from. And I would add, it's not your start point, but if you need to constrain the diameter of the shaft, it may mean that you physically haven't got enough space to put the machine in to get it out. So in which case, this would be the end, if you like, the under ream section, and then you can actually dig in or mine a heading back out, and then the thrust wall can be constructed inside that with a thrust plate on. This is the wrong way round, because you'll notice that the rig is there. This is demonstrating the theory. So in this instance, to be able to get everything in and launch it, they need a bit more space. So that's a forward shunt or a forward adder has been created, but you would do exactly the same at the back. Whether it be a case on a secant or a diaphragm wall shaft, it's very much the same. You can see that the back wall is cast. The units are in there now. Generally speaking, the precast concrete units, can take a little bit more than the sheets. The reason being is when you put a load into it, it starts to act in the hoop. Whereas if you've just got your sheeted wall, you're relying on the resistance of that sheet and the ground behind it. But you can see there. So typically you get a little bearing area if you set 45 degrees off, and that will give you the surface now. You can look at the ground there, and if you've got a good hard clay, or of course if you were in rock, you probably kind of got no problems. Interesting to know that and I'll pick it up on this slide, but it's always worth bearing in mind that you have to look at these things in a bit more detail if you've got limited cover. So if you were in a situation where you were doing a job and you were only 4 or 5 metres deep, so you've not got a lot of overburden and the ground wasn't particularly competent, you just want to make sure that when you put the load on there and you start to transfer pressure or load through whatever lining you're using into the ground, that actually you don't start to heave the ground. And in tandem with that, which would apply to all of these methods, remember you need to look at the loads that you're dealing with if you've got surfaces behind you. So any load coming down through there into the back wall ultimately gets pushed out. So if we've got, for example, a high pressure gas main sitting there, you need to be thinking about that, and possibly designing the back wall, in such a way that it could take a lot more load. So just a couple of examples. So that's a case on with in this instance the loads are small, so the back plate is sitting on the lining, and this is a diaphragm wall shaft, so a big D wall shaft, and you've got a concrete back wall on the back there. Again, this was about 1200 mil thick, so inherently the diaphragm walls have got a lot more in the way of robustness, should we say, for the jacking loads. I think that one was designed for something like 1200 ton jacking load. Something that we do quite often is the use of columns. So if you need to spread the load, because of course, looking at the thrust coming down on the other sketch there, the load is concentrated over a certain area. So if you can try and spread the load up through the rings, you can get benefit, and that's done by introducing some steel columns. So yeah, a couple of pictures there. So you can see this is the shaft, and these are the columns when it's just been put in before the machine comes in. Then the rig gets put in, shutter off the sides, and you cast those in concrete. So the action of that when that's loading up and when it's pushing the pipe this way, then you can take benefit up through the rings, help to distribute it, and then after that, the back wall can be broke out, the steels can either be burned away or they can be sacrificed, or most contractors I'm sure will want to get them back wherever they can. And then lastly, there's a use of a plug. It's probably not the best sketch in the world, but essentially what you're doing is that you've got the machine and the load will be coming through again onto a back plate, and then it may be that you've got some steels in there pushing onto the wall, but importantly this thing it's a frame or a structure is actually bolted down onto the slab itself, so as the thrust comes there, it's being restrained from going backwards. I've done this several times. One of the problems that you do have, in this instance, it's almost a combined effect, because if you can consider that you'd be pushing onto there, so yes, these would be doing an awful lot of work. You're relying on the bolts then to really take, in shear almost, the load. In this instance, it would be that you'd have some benefit from the back wall if you were pushing there. But I have seen where it may be that you don't want to load that back wall at all. I have been involved in the past where this structure, if you like, it's been a bigger shaft. It's been a bigger shaft, sorry, and the actual frame has been bolted, if you like, in the middle of the base with no connection to that back wall. And again, I'm not that keen on them personally, because again, you're relying on these connections doing an awful lot of work. I'd be more inclined to actually cast stuff in, to take some big members, big sections, and cast those into the base. I mentioned earlier about the PGA design guide. So this document, I mentioned the other one, this document is currently being updated at the moment. It's quite nice insofar as many of the things certainly I've talked about today are included in there. And towards the back, there's firstly there's some reference material with a couple of the sketches that I've put in, but also there's some worked examples, so you can see the things I was talking about earlier. So face pressure, and this is relating to that slurry pressure that I was talking about in the front of the machine. And then there's the face load. So again, it gives you a little bit of a description. So it talks about the face load, and I think I said it should say somewhere, yeah, about resistance on the cutting edge and on the shield and a bit of friction. But it gives you the simple calculation. So at least, you know, it's a starter for 10. I mean, I would always give you the helpful warning on that these were, they are a set of work calculations in order to try and give some guidance and some advice on what things are looking at. Well, since that document was written, machine technology has jumped on, no end. So what I'd always say is, if you were sitting down to look at the concept and the feasibility of a project, and you wanted to start trying to chew a few numbers, by all means, that's what the document was there for. But I've said it a few times, I'll say it again: speak to your contractor, make sure what you're assuming is correct, and indeed is that how the machine is working. Dickie mentioned earlier, these machines work in different ways, and you need to be 100% sure that you're understanding how it's working, how it's mining, and where the load might come from. And then finally on there, pipe friction. So again, that's the same. So, you've got they've got a lubricated pipe, so they've actually took the buoyant weight. In this example, they take the buoyant weight, and then they take the buoyancy effect off the pipe, and they get a net force on the tunnel. And then they're using friction factors. Again, it's included in the guidance. Just be mindful of the friction factors, because I've had it before where you might do a drive and then the loads go a little bit higher, and then people will start looking back and quoting the guidance. The 0.5 to 2.5 tonnes per square metre, as we mentioned earlier, that is it's a general guide. It's kind of a bit empirical, if you like. It's based off experience. You will get much lower loads, but by the same token, you could get much higher loads. So just in terms of how the thing works, again, in all those scenarios, the back wall is exactly the same, and what that develops, whether it be up on the column or just through the localised section itself. So you work out an applied pressure envelope, and it's in its simplest form, as you would do for an embedded retaining wall, a sheet piled wall, or a shaft. You work out the allowable bearing pressure envelope, or your bearing capacity, basically. As I say, if you were to turn this whole thing on its side, you're looking at a pad foundation, in essence. And as long as your applied pressure envelope is less than your allowable, then you should be fine. Okay.
Thank you, Jim. Any questions for Jim? Burning questions right away? It's very entertaining when the thrust wall goes backwards instead of the machine going forwards, if it's not your job.
Yeah.
That would be an entirely true, yeah.
Yeah. Thank you. Right, Graham again.
For the final time, you'll be pleased to know.
Talk about the pipe jacking operation.
Okay, so I guess this is trying to pull together some of the stuff that we've looked at, so there'll be a bit of repetition, but hopefully it'll consolidate some of the learning that we've had this morning. Okay, so again, the clue is in the name, pipe jacking. It's all about jacking pipes into the ground, and as an operation, it's a cyclic operation. The pipes come in X meters long, somewhere between 1 metre and 3 metres in length. And every time that you inject, you push one pipe into the ground, you've got to retract the rams, disconnect all the services to the machine, drop a pipe in, reconnect all the services, restart the pumps, restart the tunnelling operation. So it is a cyclic operation. And these are again just a couple of photographs. This is another picture of the same ram set in a different shaft, I think. And one of the things we've not spoken about is the entry eye. So like the sheeted pit needing to be sealed, the junction between the pipe jack and where it exits and enters its reception shaft, there needs to be a seal. Now generally what these are is a steel plate with a circular hole in it, which is slightly bigger than the pipe, and then you have a set of plates which trap a rubber. The rubber has a hole in it which is smaller than the pipe of the machine, and as the pipe goes through the rubber, it deforms the rubber, and the rubber grips the machine. Because it deforms into the ground, any groundwater load or pressure behind that seal actually forces the seal back onto the pipe, and in that way you create a seal. And this is to resist groundwater ingress into the shaft, and also to maintain your lubrication so that you don't want to be losing lubricant into the shaft, and to retain the slurry pressure in the face. Just back to the separation plant, one of the problems with losing lubricant into the shaft is that you often have your pump in the bottom of the shaft going back into your separation plant, and some of the lubricants that are used are also flocculants. So you might actually end up overdosing your settlement system without even knowing it if you're losing lubricant. This is a similar arrangement under an airport crossing, and this is a seat and pile shaft. But the general arrangement is set of jacking rams, entry eye, front wall, back wall, control cabin. So I'm hoping that we can, this hyperlink's going to work. So just while that opens, PJA, we have a website, and there are various free guidance documents and things you can download there. For some reason we've got it on the laptop but not on the screen. Do I? Can't do it from here, I think. Does anybody know how to drive the hang on, I think I might have found it. Hang on.
He's done that.
I've got it on the laptop. It's just I think you've got it on presentation rather than.
No idea.
I don't know how to drive your laptop. Anyway, so on our website, I could, if you wouldn't mind, yeah, I just don't know how to. It's not my laptop. There are a number of links and documents available. So there's the guide to best practice. There's the design guide. There's an introduction to microtunneling. Yeah, I think you had it. And there's all the research that the PJA have funded over the years. There's actually a copy for everybody to take when you leave out on the desk out there, which is the guide introduction to.
You sorry? No?
That's the screen.
Say Leon, close up.
Don't
You see it?
you just love this?
I got no idea.
It happens every time. It usually happens to
Bill
me.
Gates said to his people, When I closed the top of my laptop, I just wanted to shut down. Sorry, Bill, we've lost the coding. We don't know where it is.
Is it on the
Excellent.
I love this. Just remember, this has been brought to you by the same people who say we're going to have autonomous cars. And they ain't going to crash. I'm too much of a Philistine, but...
I think Graham just tried that, didn't he?
Thank you.
Yay.
Apologies. So we'll this is our website. You can get anything on there for free. But I think the best way of showing the pipe jacking process is probably to watch.
The following animation shows the installation of new sewer pipes DN600 in an urban crossroad with dense traffic. The whole construction site can be located in a way that only one lane is blocked. The first stage, the area around the starting shaft is cordoned off to divert the traffic. Due to the compact design of the machine and the small diameter of the starting shaft, there will only be minor disruption to the traffic flow. In this case, the starting shaft consists of a round shaft of reinforced concrete with an inner diameter of 3.2 meters. The compact jacking frame is then placed into the starting shaft, and the slurry discharge pump is mounted on a platform adjacent to the jacking frame. The operating container with the control panel and the hydraulic power pack is located on the top rear side of the shaft. A pipe stalk is then established and maintained in front of the shaft to feed the shaft crane. The slurry feed pump and the slurry discharge pump are connected between the shaft and the control container, and then connected through the separation plant to form a closed slurry circuit. Large stones are crushed by the discs of the cutting wheel. Sometimes fragments are being driven out to the surrounding soil. The product pipes are lowered into the shaft one after the other and connected with snap connectors. The jacking frame works in 3 stages. After approximately 1/3 of the maximum piston stroke, the jacking arms return and the main thrust ring of the jack can advance further. After jacking the product pipe, the connecting hoses, which connect the TBM to the container, are disconnected. The jacking frame is returned to its original position, and the next product pipe is connected. This procedure is duplicated again and again until the whole drive length is completed, reaching the reception pit. Crossing pipes in buildings are no problem with this technique, as they can be easily overpassed or undercrossed. Thus, the machine arrives in the reception shaft exactly at the planned coordinates. In our example, the total of 150 meters of new pipes could be realized with only a minimum of disturbance in a difficult infrastructure. The conventional open laying of pipes would have caused major disturbance and annoyance for traffic and the residents.
Okay. I'll try to draw us together all those things. And then I just want to play you this one because it's a lot easier to see than it is explained. And this is an animation of an interjack and how it works. Press done. I have done.
At some point during a relatively long drive, the required jacking force may exceed the capacity of the main jacking system, or the structural capacity of the pipe or thrust wall, requiring the introduction of one or more intermediate jacking stations, or interjacks, to evenly distribute the jacking load over the length of the tunnel drive. Interjacks are placed between sections of pipe and move forward with the pipeline, but are not activated until their operation becomes necessary. At such time, the first interjack is opened, advancing the microtunnel machine and the front section of the pipeline. Then, the main jacks in the drive shaft are actuated, causing the closure of the interjack, while advancing only the rear section of the pipeline. This is repeated for each interjack in turn for the duration of the drive, and upon completion, the hydraulic jacks are removed and the pipeline closed up, leaving, in effect, standard pipe joints.
Okay. So now we need to get back to the presentation. How long have classes on? Right, okay. So I think those videos are far more instructive than me just talking. So these, again, Jim's mentioned using beams to increase jacking load capacity at the rear of shafts. One of the things that needs to be considered when sinking shafts and the depths of shafts and the top of base plugs is that you need room beneath the pipe invert to take the seal and to allow the jacking rig to be placed below the pipe. So it's not a simple matter of a straight line out of the bottom of the pipe. You normally have maybe half a metre clearance between the invert of the pipe that you're jacking and the top of the base plug. And in some instances you might be recovering a machine at a much higher level within a shaft, because that's the inlet of a sewer pipe into a pumping station. That's Newark again. Yeah. So, as I mentioned earlier, break in, break out. So this is a picture of an entry seal, but with a pipe break to resist re-emotion of the pipe due to ground loading or water pressure. Break in and break out are the most dangerous, risky operations of any microtunneling operation in water-bearing ground. And the groundwater can be controlled in any number of ways. So you can use ground treatment, whereby you might grout the ground. You can use depressurisation with dewatering. You might use a second physical barrier with a concrete wrap, or the GRP plate that I mentioned earlier. And you would want to do both of those things. It's as important, but not quite as critical on the recovery side. But at launch, it's absolutely critical that that's controlled. Pipe handling is a part of the process that is very important. So you don't want to be damaging your pipes. Your pipe jacking operation is very much influenced by leakage. So if you damage a joint, or you don't make the joint properly, and you've got leaking joints, you've got water coming down the invert, you'll get loss of lubricant into the tunnel, which causes some of the problems I mentioned earlier. You might have higher loads, you might have lubricant going into the separation plant. So handling the pipes carefully, putting the seals on very carefully, jointing the pipes carefully is an inherent part of the process, very important. Most pipe manufacturers will supply pipes with proprietary lifting. I'm not sure whose this is. I think this might be one of our Middle East members. But they normally have a cast-in lifting point. Some manufacturers just use a whole bolt-on plate, which is very simple. Some use cast-in items. Where the simple hole is used, it's often duplicated as an injection point as well. So this is a picture of an interesting project in London, where a new pumping station has two incoming feeds from very different directions. So we've got one microtunnel being set up here with a back wall there, and one microtunnel being set up here with a raked A-frame to take the load into the base plug to be driven here. Now, both of these drives were installed simultaneously. So this is a complicated bit of work, I guess, because at the top of the shaft we've got a separation plant, got a control cabin, we've got a crane, and because it's a discontinuous process, you can be changing a pipe on this drive whilst you're driving this pipe. So as long as your pipe change time is similar to your driving time, you can do both at the same time. It's just an interesting example. So it shows you a number of things. You've got one type of back wall there, completely different type of back wall there, and two drives being driven at the same time. And these lads move from there to there to there. They never get a rest.
Plan that up on separation.
Yeah. Just switching between the two.
For women's.
Sunday, it's the first time and last time we've ever done it. It worked. And just some more photographs. That's the favourite pipe jacking photograph with the 6 rams and the slurry lines coming through. Machine being lowered into the shaft for launch. Just and a nice picture of a curved pipe jack in Albrighton in the Midlands, just before Mr. Dexter gives you his long distance and curved pipe jacking tool.
Any questions for Graham before we move on to Richard?
Just seeing that theodolite in that picture there, on the larger pipes here, you're using line and level, so they feel like the track where you're going. On a smaller diameter, how are you tracking it?
We just use a pipe laser because the drive length's relatively short. So a 600 machine will, in the best conditions, probably do 140 metres. You wouldn't really want to be designing it for that. No, I'm just saying, you wouldn't want to design it at 140, you might want to design it at 100, but it could. So it's well within the capabilities of a standard pipe laser. Over that distance you start using a theodolite and a higher grade optical laser. And then after that you'd use a gyro. I'm sure Richard will be talking about gyros for curves.
Go back 2 pictures. It dawned on me that nobody had actually... Go on, one more. The picture on the right-hand side happens to come off our website, and everybody has talked about thrusts and load and jacking and all the rest of it, and nobody's actually mentioned a tonnage. Those 6 jacks are 1,500 tonnes capability. They are devastating if the back wall goes bang. Standard interjack will do about 300 tonne on a fair-sized pipe.
Well, we've had...
Yeah, I'm not going to say, hey, your woes are your woes.
I think the fair point there is the 1,500 tonnes, and that's all going through the pipe. Unless
Yes.
they interject it.
Yes.
You know, but so the point this morning about the temporary loads on the pipe, often that is the critical load, is the jacking.
For sure.
There's a young man just there going to do a description of a very long
Good.
line. I'm going to talk about long ones. So,
Thank you, Graham.
okay.
It's your marathon stint done for.
Yeah.
Back to
I wonder why he got it all over and done with in one go. What we did here. How do we fix this? Okay, so I know it. Super.
That's always good.
Just another one, we were talking earlier about the ground coming on, and somebody mentioned that even strong ground and strong materials move. If you go down the very deep South African gold mines, 3 kilometres deep, the core site, which is 300 megapascals, so 10 times stronger than any concrete you generally deal with, will move a foot in 10 years. It's plastic at that depth. You'd be staggered what it is. Okay, I was asked to do long and curved, but I'll also add a third one in, although I haven't really done a presentation on it, and that's big. For some unknown reason, and bear in mind I am in the PJA, the UK tends to get very cautious around 2.1 metres internal diameter, 2.4 external. As a company, and if you go to anywhere in the Far East and all the way up the GCC, so from Oman all the way up to Kuwait, 3 metres, 3.2 metres, even 3.6 metres is not an unusual diameter for a pipe jack. I didn't put the animation in. I thought I'd fail. And okay, typical microtunneling you'd see in a city job centre. Okay, we'll do guidance first. So we'll do curve drives and how you can do them, what you can do, and so on and so forth. That's the typical output you'll get on the inside of most control containers, whether they happen to be Heron Connect or Iseki or the manufacturers. So some version of where you are and where you're aiming and where you want to be. That's the ELS laser guided system. So somewhere in the shaft bottom is a laser. It's been set up by an engineer, it's been checked. Somebody's made sure that the grade you've dialed in is the right way round.
Why are you looking at me?
So the gang aren't sitting, I can hear it, and it comes out up here. Pretty known about, as Graham mentioned, it'll do you 150, 200 metres. High spec theodolites with laser through the eyesight will get you about as far as 300 metres. And when you get further than that, you're into all sorts of stuff. So, typical shaft, you'll have some form of target, some form of laser station, you have a wheel to measure distance, and some sort of reference module normally for levelling. Hydrostatic water levelling system, so it tends to be on the bigger machines. Curve drives. Okay. Curve drives you can do. As a rule of thumb, do not go designing pipes which are 2.5 metres long in this country with a 1 degree angle of deflection. You will break them. I know you can do it, but the problem is, as Jim and Graham both illuminated, you will have a wobble on your pipe jack. Nobody steers it perfectly online. And those wobbles will exacerbate whatever you put in as a curve. So if you can design your curve, roughly speaking, if you were going to put a 4-foot pipe in, 1.2 metres, it has approximately 1.5 metre outside diameter of the pipe, you will do a radius of 150 metres. If you're going to use a 1800, that's 2.1 outside, about 200 metre radius, 2.4, etc. So roughly speaking, the outside diameter, if it's 1500 millimetres, knock a zero off, that's the kind of radius you can do with a curved pipe jack. Do not put it straight after the exit from a shaft. Give a tunnelling machine some time to run in a straight line. So it can get in the ground, you can get the loads bedded in, the jacking frame can get bedded in, and you're not trying to dissipate load very, very soon after the shaft bottom by inserting a curve. So the best curved pipe jacks will go several hundred metres or 100 metres in a straight line and then start curving in whichever direction. When you go long distances and when you go curved distances, the tunnelling machine or the centre of the tunnelling machine or the target tends to go out of the range of whatever laser system you have. And for those types of application, you're going to go into a gyro compass system. This needs checking. It drifts. The Earth's magnetic field, which is what it works on, you set it up on the surface, you fit it, and and you check it regularly, because it will drift. There's a drift angle on it, and as it curves, the odd bit is the drift angle will change slightly, because it's going across the magnetic field often. That's roughly the inside of a working curved pipe jack, as opposed to a nice clean one. I suspect, what's that, about 1500, 1800? Something like that. They can be done. There's no reason you can't do them. Engage with a professional contractor. Where a lot of people tell you can't do this, you can. If you're going far enough and big enough and long enough, you can even do reverse or double curves. But you are starting to get into cleverness where you need a clever, professional, responsible contractor. Not every Tom, Dick and Harry will take on a double curve or even a single curve. It requires people with skill, talent, by and large the experience to do it. Okay, again, in the United Kingdom we have a historical professional fear of any number greater than 500 metres. There are and have been pipe jacks and microtunnels done over that distance, but they are few and far between. Zublin did one in Coppermills in the either early 80s or late 70s, I can't remember. Streeters, as they were called, did one in Blackpool, 700 metres with a double curb with an EPB machine. Graham and I used to work for a company called Joseph Gallagher. They did a kilometre just under in Brighton. And probably the most recent was a talk about a little bit later, so I shall not go into that. Okay, we'll go up to what long distances you need to do in order to achieve them, and what brings success. Now, a lot of it is, Graham's done some, Jim did a lot of it. Okay, long pipe jacks are all about thrust and lubrication, and this is not a pornographic talk. They're about how much force you can mobilise and how little friction you can keep off the top or round the pipe. I have seen pipe jacks that were 300 metres long with 1,200 tonnes, with the rear wall smashed, and with the application of vast quantities of various forms of lubricant, we got the 1,200 tonne jacking force down to less than 500 tonnes. Remobilised the whole lot and finished the drive at about 350 metres. So a lot of this is to do with utter dedication to lubricating the external friction of the line. There are various automatic lubrication systems that will lubricate constantly as the machine is working. And then on top of that, you get all sorts of personal preferences to what you do and how you do and why you do it. So, skin friction, available jacking force, obviously the nominal diameter of the jacking pipes, automatic lubrication systems, the frictions between the pipe and the skin and the soil and all the rest of it, plus the number of interjacks. Again, you can either calculate it, which would be the logical way. Most people calculate it and or base it on an amount of experience. Traditionally, the first interjack you would put very close behind the back of the microtunneling machine. If you're going very long distances, it's also recommended, point number 8, I'll highlight that. Most of the manufacturers will make you a thrust unit that goes directly behind the back of the microtunnel. Under normal circumstances, the microtunnel is being pushed by the jacks in the pit bottom if you can get away with it. Sometimes you have to push it with the interjacks. Most of the time, if you can get away with it, you will push it, regardless of how far you're going, with the jacks in the shaft bottom. When you're going a long way, it's not possible, because the interjacks you have in, you can often get into double figures. If you're going to a kilometre, getting to a double figures in interjacks is not unusual. So in order for the machine to operate and to cut properly, you end up with a thrust can behind the back of the tunnelling machine, as well as all of the interjacks. But it's not unusual for people to put interjacks at 75 metres, 100 metres. Rarely do they go much longer, distance between them and 125. But it sometimes comes down to personal preferences. So, one other thing, if you're going a long distance, face access with or without hyperbaric capabilities. I don't know, hyperbaric diving, working in compressed air. When you start going long distances with any tunnelling machines, you are going to wear the teeth out, unless you are in the most forgiving of ground. So some access, there's a door, so you tend to be 1500 diameter, 1800, 2100, tend to have face access doors. You can have the equipment with a hyperbaric can, so people can go inside the tunnelling machine, compress themselves as if they're in a diving environment, decompress themselves as well, and then enter the chamber, which is under water pressure. Change the teeth, come back out, close the door. Again, lubrication, reduce the friction. You're always reducing the friction. It gives you your best opportunity to go longest distances. Automatic mixing, automatic injection, and automatic sequential valves for doing all the injections. That is an interjack, or what the inside of one looks like. So there's a series of intermediate rams. Both Jim and Graham have described the steel can, the concrete can, and they're the interjacks that basically oscillate. And the whole pipeline looks like a caterpillar. That's a telescopic can that goes behind the back of a tunnelling machine. Most environments, most places where you meet microtunneling and pipe jacking, you will never see one of these. They're simply not long enough to justify the cost of one or the requirement to even have them. But on long drives, kilometre and more, they're essential. Bryn's going to talk about that in a minute, but that's obviously as our company. That's a great success in the United Kingdom. And again, highlight the size. So that's 2.2 internal diameter. It's 1.25 kilometres. There is no reason it can't be 3 metres and 1.5 metres. I am presently engaged with a contractor who came to us. We're in the process of selling him a 2.4 metre machine to microtunnel 1.95 kilometres on a sea outfall that happens not to be in the UK. That is a very large sea outfall microtunnelling setup, just for your knowledge. Yeah, you're looking at it thinking, where's that? Okay, and that's me done. I thought I'd keep that short and sweet, but by all means ask me any questions.
Thank you, Richard. Any questions for Richard before we go into the break?
Just a quick question about the interjacks. I've not done this before. Do you run them simultaneously, or do they run one at a time in the sequence?
One at a time. Most of the systems, most of the control containers won't let you run more than one. But as with everything that runs off PLC, you can have it altered if you so desired. There is a reason for that. When pipe jacks start getting very long, and you do start ending up with having to take your shoes and socks off to count the interjacks, you get to the stage where the interjacks become self-fulfilling prophecy. They start defeating the reason for going longer and the reason for using it as a microtunnel rather than a normal tunnel. Now, the difference between a normal tunnel of 2.4 and a microtunnel of 2.4, 1/4 of the number of men, 1/10 the amount of settle time, half if not a quarter of the number of men in the yard, quicker, faster, and nobody underground almost, a couple of blokes, that's all you're looking at, and they're in the pit bottom. And the number of times you go into the tunnel, rare. So the reasons economically, commercially for using a microtunnel are just there. But for some reason when you come into the UK, as soon as you get 8 foot, well 7 foot, 2.1, people go really nervous about doing microtunnels over any great length.
That reduced number of men is also a safety benefit,
Yep.
because you've got much less man-hours on the project, and therefore
Yeah.
less accidents.
So
Less potential for accidents.
one of the things I'll deal with, I've got one to do afterwards, is, and this is not a criticism, it's getting the clients to come on board with what technology really is out there. I worked in the Middle East, and I worked for a company called Kuwait Oil Company for a period of time, or as a subcontractor to them. And they asked me, is your tunnelling machine here in Kuwait? And like all good contractors, I lied through the back of my teeth and said, yes, of course it is. Could we see it? At which point I started getting nervous. Yes, of course you can. When would you like to see it? Well, we can't make tomorrow, at which point my heart started beating, thank God for that. Yes, I had to phone our yard, which was in Bahrain, get the tunnelling machine put on a lorry, driven to Kuwait, and the lorry and the crane that had unloaded it and put it on the floor was there on the floor, was parked next to it, and the guys from Kuwait turned up and said, oh, that's wonderful. Keep that here for another 6 months until we start our project. Oh yeah. Getting clients to understand and know and fully appreciate what the machinery, what the technology, and the kind of advancements that have gone on, curved drives, long drives, large drives, cost saving, risk saving, time saving, and it's all there to be grasped, but it's always the same problem. Have you done this before in the United Kingdom? Well, not quite.
Any more questions for Richard before we go to the break?
Yeah, how are you forcing the curve? Is the head articulated?
Yeah.
Oh.
Sorry, apologies for not dealing with that. I will deal with it, actually.
It's a good question.
It is a good question. See if I've got a photo with a tunnelling machine. Right, there's a joint there. There. See in the middle? Right, that's approximately 75mm articulation joint. If you get this tunnelling machine fully articulated and carry on and with it fully articulated, you'll be breaking pipes for fun. The machine will steer, and that's one of the reasons I say always be careful with the minimum radiuses. Be very, very, very careful specifying 1 degree. The pipe manufacturers will tell you you can do it, and you can, but it reduces the pressure you can put on the pipes by something like 80%. All you then need is a little wiggle while you're going around the curve, and you've taken 1% to 2%, just over a 10-metre stretch. And at that point, myself and the gentleman in the room recollect very carefully, you start breaking pipes. And when you're only 3 metres from the seabed, that's kind of worrying. So you have to be careful. Engage with your contractors, engage with your consultants. It is possible to do it, but it requires careful planning, and it requires careful risk evaluation and careful allocation of risk as well. So,
right, okay, thank you. With that, we'll close the session. Please all come back for 3:30 after the break, and thank you to all of the speakers in that session. It's been very, very illustrative. Thank you.